Hey people, let's start learning for earning.
Traditional linear electronics process data using mere milliwatts of power. Industrial power electronics control massive megawatts of physical energy. Linear components operate in an active region to smoothly shape low-voltage signals. This continuous partial resistance naturally dissipates a small amount of heat. Operating in that active region while carrying an industrial electrical load would melt the hardware. To survive the energy transfer, power components must act as high-speed digital switches, alternating strictly between complete cutoff and full saturation. Safely switching these currents requires precise engineering of the semiconductor material at the atomic level. To understand how this works, we will first examine the material science and atomic doping that makes switching possible. Next, we will map out specific power component architectures and the precise voltage current characteristics required to trigger them safely. Finally, we will outline the industry's transition from standard silicon to silicon carbide materials. Controlling modern physical infrastructure means dictating the behavior of individual atoms. Standard conductors allow continuous current, while insulators block it entirely. Neither functions as a digital switch. A pure silicon crystal is a natural insulator. Its electrons are locked tightly to their host atoms. Exposing this crystal to thermal energy causes the lattice to vibrate. A few electrons break free and wander, creating a slight unpredictable conductivity known as the intrinsic state. Engineers control this conductivity through doping. By deliberately injecting foreign atoms into the lattice, they alter its electrical properties. This creates a permanent surplus of free-floating electrons, forming an N-type semiconductor optimized for negative charge. Injecting different elements creates structural voids, known as holes, where an electron ought to be. This forms a P-type semiconductor. Joining these materials creates a P-N junction. At their boundary, electrons drop into adjacent holes, forming a depletion region barrier that physically blocks current. Applying external voltage makes this barrier vanish, allowing a wave of electrons to flow through the block. Standard PN junctions handle the 5 volts running through a computer processor perfectly, but expose them to the voltage of an industrial power grid, and they vaporize. Forcefully turning off a semiconductor while it is under hundreds of reverse volts triggers a physical breakdown in standard logic architectures. The power diode addresses this through a specific alteration of the internal semiconductor geometry. Engineers expand the component, sandwiching a lightly doped N drift layer between the P and N regions. When the switch cuts off, the resulting electrostatic surge hits this thick layer. It acts as a physical buffer, absorbing stress and keeping the outer boundaries intact. This structural protection creates a mechanical delay. The wider physical distance increases the time it takes for the internal charge to clear out, slowing down the diode's recovery and turn-off time. For industrial applications requiring high switching frequencies, even fast recovery diodes are too slow. The industry relies on the Schottky diode instead. The Schottky diode replaces the entire P-type semiconductor with an aluminum-silicon metal junction connected directly to the N-type material. This removes the slow recovery time associated with holes, driving turn-off speeds down to the nanosecond range. By modifying the internal geometry of the semiconductor, engineers trade raw voltage capacity for switching speed. This geometrical balancing act led to the IGBT, the insulated gate bipolar transistor. It is a hybrid device, pairing the fast, low-power control of a MOSFET with the heavy current handling capacity of a bipolar junction transistor. Looking at the physical terminals, applying a control voltage at the gate terminal commands a power flow between the collector and emitter. Safely directing that flow requires microsecond timing. During the T-on phase, collector current surges exactly as collector-emitter voltage drops. In the T-off phase, current collapses while voltage spikes back to maximum. If this timing slips even a microsecond, the thermal load will destroy the component. The IGBT also carries an inherent risk known as latch-up. Its 4 alternating semiconductor layers form an internal parasitic PNP transistor. If the current exceeds a specific threshold, the structure locks into an uncontrolled on state. Manufacturers tune the specific geometries of the layers to suppress this effect. For managing the largest industrial loads, engineers use the thyristor family, specialized 4-layer PN-PN devices built for self-controlled high-power switching. Inside a heavy industrial control cabinet, massive thyristor arrays are bolted directly to heavy copper bus bars to route facility-level current. They select the silicon-controlled rectifier, the bidirectional triac, or the gate turn-off thyristor. The MOS-controlled thyristor features a specific triggering mechanism. Unlike most standard devices, the MCT requires a negative voltage pulse at the gate to initiate the turn-on process. IGBTs and thyristors successfully manage megawatt current loads, provided their internal layers are driven with perfect microsecond timing. Traditional silicon has reached a physical limit in high-frequency, high-temperature applications. It cannot operate at these extremes without succumbing to thermal breakdown. To push past this limit, the industry is migrating to wide bandgap materials, specifically silicon carbide and gallium nitride. While a standard silicon lattice breaks apart under heat, the superior atomic bonds of silicon carbide resist intense thermal energy and maintain structural integrity. This diagram shows the practical result of that atomic resilience. Switching to silicon carbide yields an 85% reduction in switching energy loss compared to traditional silicon IGBTs. Because SiC components dissipate far less heat, engineers can build smaller, lighter modules and eliminate heavy liquid cooling systems from the final design. The adoption of silicon carbide is the material science breakthrough required to build next-generation energy grids. This diagram illustrates power electronics as the functional hub of modern infrastructure. These microscopic switches drive high-voltage DC transmission lines, maintain industrial welding arcs, and regulate uninterruptible power supplies. Electric vehicles present a high-stakes environment for thermal and electrical stress management. The green power electronics module sits directly between the battery block and the electric motor. Converting the DC power from that battery into the AC power needed to spin the motor relies on atomic doping, injecting foreign atoms to make switching possible. The physical geometry of the integrated N-drift layer is what absorbs the severe electrostatic stress, preventing the raw battery voltage from destroying the component. The exact microsecond timing of the voltage and current dropping across the IGBTs ensures the motor receives a precise drive signal, and utilizing wide bandgap silicon carbide materials prevents the entire module from failing under the thermal load. Software algorithms tell automated systems what to do, but the physical manipulation of heavy industry is governed by the microscopic physics of power electronics.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.